Today we will be discussing about hydraulic pumps and hydraulic turbines. First we will see hydraulic pump. So a hydraulic pump is a device which raises liquid from a lower level to a higher level by utilizing the energy supplied to it. So basically the pump will be consuming mechanical energy which it receives from a motor. The motor consumes electrical energy and converts it to mechanical output, which is the rotation of the shaft, and that shaft will be coupled to the hydraulic pump. So the pump utilizes this mechanical energy to raise the fluid from a lower level to higher level. Since we are dealing with hydraulic pumps, our working fluid will be water. So hydraulic pump is a device which utilizes the mechanical energy to raise the pressure head of a fluid, or it raises the liquid from a lower level to higher level. So mostly the pump is hydraulic pumps are used in agricultural works, irrigation works, then in water supply and drainage systems, hydraulic pressure machines, etc. Hydraulic pumps are in general classified into positive displacement pumps and rotodynamic pumps. So, what is a positive displacement pump? A positive displacement pump, it takes liquid and then pushes it by exerting a force on it by the movement of a mechanical member, which results in increasing the pressure and thereby lifting the fluid to desired height. So here the mechanical member is usually called as a piston. Example of positive displacement pump is reciprocating pump. Next one is a rotodynamic pump. In rotodynamic pump, the liquid passes through a rotating member called impeller. Due to the rotation, angular momentum of liquid changes, which increases its pressure. So the developed pressure enables the liquid to be lifted to a higher level. Example is centrifugal pump. So here we will be discussing about both reciprocating and centrifugal pump. So first one is centrifugal pump. Now, centrifugal pump is a device which is used for low head and high discharge applications. The centrifugal pump usually has high efficiency and output. Major components of a centrifugal pump include a rotor, which is usually known as an impeller, then it has a casing, then a suction pipe, foot valve, delivery pipe, and delivery valve. Along with this, a priming valve will also be present. So these are the major components of a centrifugal pump. Now let us see this figure. In this figure, you can see a strainer over here, strainer, then foot valve, then this is a suction pipe. Here you can see a suction gauge. This is a suction gauge which measures the suction pressure. Then coming to this point here, we have a shaft. This is known as eye of the impeller. So in this shaft, the shaft of the motor is coming and is coupled to this shaft, and this is known as eye of the impeller. Then on the eye of the impeller, we have the impeller. This total. This is the impeller, and these are impeller vanes. Impeller vanes. This is the casing. This is a special type of casing known as volute casing, and here we have a pressure gauge, then a delivery valve, delivery pipe, and the overhead tank to which water has to be raised. Now here we have one more valve present here, which is known as the priming valve, which is used for priming. So priming, P-R-I-M-I-N-G, priming is a very important process in centrifugal pump, because once the centrifugal pump will work only if the pump is primed. Priming is the process of filling the suction pipe, casing, and delivery pipe up to delivery valve with the liquid to be pumped so that no air pocket is left. Now after priming, you can start the pump. So starting the pump means you will be switching on the motor. So the motor consumes the electrical energy and produces mechanical output, which is rotation of the shaft. That shaft will be coupled to the shaft that is present here. This is eye of the impeller, and this will rotate. So once this shaft rotates, the impeller will also rotate. The casing is already filled with water. So the water angular momentum will be imparted to water, and the water will rise up. So once the delivery valve is opened, it will raise up to the overhead tank. So once the water which was present here leaves, a pressure difference will be created here. There will be a pressure drop at this point. Now this pressure drop, now here you can see outside here atmospheric pressure is acting. Now due to this pressure difference, water will move up through the strainer, a foot valve, through the suction pipe, and reaches here, and then again the process continues. This is how pumping happens in a centrifugal pump. Now here you have a strainer. The function of the strainer is to prevent the dirt or leaves from entering into the suction pipe. Then we have a valve known as foot valve. Foot valve is a one-way or a non-return valve. That is, it allows water to flow only in one direction, that is the upward direction. Once the water has entered, it cannot go out. So this is a one-way non-return valve. Then suction pipe, through the suction pipe the water comes up. Here we have a suction gauge which measures the suction pressure. Then water comes to the casing. Here the impeller rotates and the angular momentum is imparted, due to which the fluid rises. Here the delivery gauge measures the delivery pressure. Then once delivery valve is open, the fluid will move up and reaches the overhead tank. So before starting the pump, the delivery valve will be closed, priming will be done, and you will switch on the motor so that the impeller rotates and angular momentum is imparted. The delivery valve will be open and the fluid moves up to the overhead tank. And then due to the pressure difference created here, the fluid in the sump level will raise through the suction pipe. And then this process continues. So we have a continuous pumping of water. Now water once filled in the suction pipe will not go down, because the foot valve is a one way and a non-return valve. So this is the basic working of a centrifugal pump. So based on the working head, centrifugal pump is classified into, it is actually a low head pump, but still based on its working, centrifugal pump is again classified into low head pump, which has a head below 10 meters, then medium head pump, that is 10 to 30 meters, and a high head pump above 30 meters. So priming is very important when we discuss about centrifugal pump, because without priming the pump will not work. So you have to do priming either with a fluid having a density same as that of the fluid to be pumped, or a fluid having higher density. Usually priming will be done by using the same fluid that is to be pumped. Now certain aspects related to centrifugal pump. One is suction head. Suction head is the height from the center of the pump to water level. So here water level in the from the sump to water level in the sump. So this is the suction head HS marked over here. That is the height of the center of the impeller, that is eye of the impeller, to the sump water level. Next is delivery head HD, that is the height from the center of the pump to the head of the overhead tank, from the level of water in the overhead tank. This is the suction head. Next is static head. Static head is the sum of suction and delivery head. Then manometric head. Manometric head is the total head against which a centrifugal pump has to work. So manometric head is equal to HS. HS is suction head, we have already seen. Then HD. HD is delivery head. Then HFS. HFS is the head loss due to the suction head loss, that is lost in the suction pipe due to friction in the suction pipe, because the suction pipe has some amount of friction, due to which some head will be lost. That lost head is known as HFS. Similarly, HFD. HFD is the head loss due to friction in the delivery pipe. Head lost due to friction in delivery pipe. That is, when fluid is flowing through the suction and delivery pipe, due to friction on the walls of the suction and delivery pipe, some head will be lost. So that loss in head is known as HFS and HFD. Head loss due to friction. Then V square by 2G. V square by 2G, it represents the head lost when the fluid is discharged to the overhead tank, because during the delivery pipe the fluid is flowing in a particular diameter pipe. Once the fluid reaches this point, there is a sudden expansion of fluid. Due to this sudden expansion, some head will be lost. That head loss is given by V square by 2D, where V is the velocity of fluid in the discharge pipe, V square by 2G. So this is manometric head. Manometric head is the total head against which the centrifugal pump has to work. Next is water power. Water power is given by the power that is available in the water or imparted by the impeller to the water is rho g q hm. So what is this rho? Rho is density of the fluid, that is density of water. G is acceleration due to gravity. Q is the discharge, actual discharge, and hm is manometric head. So now we have three efficiency terms. One is manometric efficiency. Manometric efficiency is equal to, it is the ratio of manometric head by head imparted by impeller on water. It can also be written as water power. Manometric head, that actually is the water power. Water power expression is given here by power at the impeller. So water power by power at the impeller. Next is mechanical efficiency, which is the ratio of power at the impeller by shaft power. Mechanical efficiency is the ratio of power at the impeller by shaft power. Next is overall efficiency. Overall efficiency is the product of manometric and mechanical efficiency. So when you take the product, the common term will cancel out. So here the common term is power at the impeller. So power at the impeller will cancel out and you will get water power by shaft power. So overall efficiency is equal to water power by shaft power. Next is a simple numerical problem on centrifugal pump. So here a centrifugal pump with a discharge of 22 liters per second develops a manometric head of 44 meter. So discharge and head is total manometric head is available. If manometric efficiency and overall efficiency of the pump are 80% and 70% respectively, find power delivered by the pump, power available to the impeller, shaft power and mechanical efficiency. So here discharge is given as 22 liters per second. So 1 liter is 1 by 1000 meter cube. So 22 liters will be 22 by 1000, that is 0.22 meter cube liters per second, so meter cube per second. Then manometric head is given, mechanical efficiency and overall efficiency is given. Sorry, manometric efficiency and overall efficiency is given. So we can find out the water power. Water power is equal to rho g q hm. We have already seen this equation. Density of water is 1000 kilogram per meter cube into acceleration related with g is 9.8. Discharge is 0.22 meter cube per second and manometric head is 44. You will get 9.496 kilowatt. Then power available to the impeller. So actually manometric efficiency is equal to water power by power available in the impeller. We have already seen that. So from this you can find out the power that is available to the impeller. Then overall efficiency is equal to water power by shaft power. So from this you can find out shaft power. So once you have so next you have to find out mechanical efficiency. Now overall efficiency is the product of mechanical and manometric efficiency. From that you can find out mechanical efficiency. So this is simple numerical on centrifugal pump. Then another question: the suction and delivery head of a centrifugal pump are 4 meter, 35 meter respectively. The head loss in suction side and delivery side due to friction are 0.6 meter and 3.4 meter. So head loss due to friction, and then suction and delivery head is available. You can find out a manometric head. The equivalent kinetic energy loss at the delivery end of the pipe is 1 meter. So there is an equivalent kinetic energy loss at the delivery of the head of the pipe, that is V square by 2G, that is also given. Find out the static head and manometric head of the pump. So static head is actually the sum of suction head and delivery head. Suction head is given as 4 meter, delivery head is given as 35 meter, so 39 meter is static head. Manometric head is HS plus HD plus HFS plus HFT plus V square by 2G. Every term is given in the question. You can add and find out the manometric head. Next question: a centrifugal pump has to lift water over a total head of 40 meters at a rate of 50 liters per second. So total head is given 40, manometric head is 40 meters. Then the discharge is 50 liters per second, that is 0.05 meter cube per second. Then find the power required to run the pump if the overall efficiency is 65%. So you can find out water power, rho g q hm. Every term required is given. So water power is 19.62. Then overall efficiency is given. Overall efficiency is the ratio of water power by shaft power. From that you can find out shaft power. So this is the power required to run the pump, that is shaft power. Next is reciprocating pump. Now reciprocating pump is actually a positive displacement pump. It creates the required lift and pressure by displacing the liquid using a moving mechanical element called as plunger or piston housed inside a cylinder. So most of the reciprocating pump have more than one cylinder for pumping. So here this is a single cylinder reciprocating pump because it has only one cylinder. This is the cylinder and this is the plunger. So most of the cases you have more than one cylinder, that is double acting. This is single acting, and then you have double acting reciprocating pump. So that is most common. So here what happens is that when the plunger moves in the right direction, that is it moves towards the right direction, the pressure in this area drops and the fluid will rise through the suction pipe. Suction valve opens and the fluid comes in. Then the plunger moves towards the left direction, so the suction valve is closed, the fluid gets pressurized, and the delivery valve opens and it moves through the delivery pipe to the required place. This is the working of single acting reciprocating pump, but here the problem is the supply will be intermittent because during suction stroke there is no delivery. So the total discharge will be intermittent. In order to avoid that, we will be using double acting reciprocating pump, where the discharge will happen at both time, because it will have a delivery and a suction pipe on the other side also. There is this side also, it will have a delivery and a suction pipe. So that is double acting reciprocating pump. Double acting reciprocating pump. So we will see some equations that are required for this pump. One is discharge. Discharge is given by LAN by 60, where L is the length of the cylinder, A is the area of the cylinder, Now area will be pi by 4 d square, where d is diameter. Diameter is usually represented as bore diameter. diameter of the cylinder is usually represented as bore diameter, N is the RPM. So LN by 60 will give you the discharge, LN by 60 will give the discharge, and if it is a double acting reciprocating pump, then discharge will be 2 times LN by 60. Then power delivered is equal to LN by 60 into rho g into HS plus HD. HS is the suction head and HD is the delivery head. Now there is a term known as slip. It is a difference between theoretical and actual discharge of a reciprocating pump. Slip is equal to Q theoretical minus Q actual. Percentage slip is equal to Q theoretical minus Q actual by Q theoretical. Then coefficient of discharge CD, it is the ratio of actual discharge by theoretical discharge. Ratio of actual discharge by theoretical discharge. Now the reciprocating pump is usually a high head, low discharge pump. Now we will discuss some numericals on reciprocating pump. A single acting reciprocating pump is running at 50 rpm. It has a bore and stroke of 150 mm. Bore is bore diameter, that is cylinder diameter, and stroke is 250 mm, that is the stroke length L. So you can find out discharge. The suction and delivery heads are 5 meter and 15 meter respectively. Find the discharge capacity of the pump and power required to run the pump. So here discharge capacity, that is Q theoretical. Q theoretical is equal to LAN by 60. We have already seen the equation LAN by 60. A is pi by 4 d square into L into N by 60. So you can substitute the bore diameter D and stroke length L, and you can find out theoretical discharge. Now power required is equal to rho g Q theoretical into HS plus HD. From this, power required can also be found out. Next question, the discharge capacity of a single acting reciprocating pump is 12 meter cube per hour. The plunger diameter is 0.15 meter and stroke length is 0.3 meter. If it runs at 40 rpm, calculate the theoretical discharge, percentage slip, coefficient of discharge, and what is the volumetric efficiency of the pump. So here again plunger diameter is given, so that is a bore diameter, and stroke length is given and discharge is given. So theoretical discharge Q theoretical is equal to LAN by 60, A is pi by 4 d square. You can find out theoretical discharge. Actual discharge is given in the question as 12 meter cube per hour. So percentage slip is equal to Q theoretical minus Q actual by Q theoretical. Now this is in meter cube per hour. You have to convert it into meter cube per second. Then you will get percentage slip as 5.67. Coefficient of discharge CD is equal to Q actual by Q theoretical. Take the ratio between Q actual and Q theoretical. Now volumetric efficiency is actual volume by theoretical volume. Actual volume discharged by theoretical volume discharged into 100. So that will give the volumetric efficiency. Now moving on to hydraulic turbines. Hydraulic turbine is actually a prime mover in which shaft torque is developed by converting the potential energy or kinetic energy possessed by liquid into mechanical energy. So basically turbines are devices which are used to produce mechanical energy. So turbines can be gas turbines or steam turbines or hydraulic turbines. In this here we will be discussing only about hydraulic turbines. So the working fluid is water. Now the water will be stored in large carriers known as dams. From the dam, water will be flowing through large pipes known as penstocks. During the flow, the potential energy of the water will be converted to kinetic energy, and the fluid that possesses high kinetic energy comes and hits on the turbine blades, where this kinetic energy is converted to mechanical energy. The turbine will be directly coupled to a generator which generates electrical energy. Hydraulic turbine consists of a wheel known as a runner having a number of curved vanes on its periphery. Based on the method of energy conversion, hydraulic turbines are classified into impulse turbines and reaction turbines. In impulse turbine, all available potential energy of water is initially converted to kinetic energy by means of a nozzle. So here nozzle is used to convert the potential energy of water fully to kinetic energy. The high velocity jet of water coming out of the nozzle strikes on a series of vanes fixed on the turbine wheels. This results in an impact force on the vanes, making the runner to rotate. So here basically the kinetic energy of the fluid is utilized. Whereas in reaction turbines, only a portion of the available potential energy of water is converted to kinetic energy before entering the runner. The remaining energy remains as pressure head. While passing through the runner vanes, it is subjected to conversion from pressure to kinetic energy. The increase in kinetic energy related to the runner results in a reaction force causing the runner to rotate. So in reaction turbines, both kinetic and potential energy is utilized. Potential energy in that will be converted to pressure head, and this pressure head is also utilized in the turbine. So here simultaneous utilization of kinetic and pressure energy happens, due to which a reactive force is exerted which causes the runner to rotate. Now certain terms related to turbines. One is net head. It is the total head that is available at the inlet of the turbine after reduction of various type of head losses, that is head loss due to pipe friction, pipe bend, etc. Head loss due to friction is given as 4FL V square by 2GD, where F is coefficient of friction, L is length of pipe, V is flow velocity, and D is diameter of the pipe, G is acceleration due to gravity. Now D is pipe means penstock, because water will be flowing through this large pipe known as penstock. Now efficiency term, one is hydraulic efficiency. It is the ratio of power delivered to the runner, that is runner power by power available at the inlet of the turbine, that is water power, runner power by water power. Mechanical efficiency is power produced at the shaft, that is shaft power by runner power. Overall efficiency is the product of hydraulic and mechanical efficiency. It is the ratio of shaft power to water power. Now Pelton turbine. Pelton wheel turbine. Pelton wheel turbine is a high head low discharge impulse turbine. First type of turbine, that is Pelton turbine. Pelton turbine is a high head low discharge impulse turbine. It can work under a head of 200 to 2000 meters. The Pelton turbine figure is shown here. So here this is the runner. So the runner has runner vanes attached on its periphery. These are bucket shaped vanes. Now the fluid, that is water, will be flowing from the dam through huge pipes known as penstocks. This water flows and it reaches the nozzle here. Here we have a spearhead. By adjusting the spearhead you can control the discharge. The fluid comes and hits on the runner vanes, and the kinetic energy of the fluid will be converted to mechanical output. The runner vane moves, the runner rotates, and the mechanical output will be produced. After this, the water flows down and reaches the tailstock. So this is the basic working of a Pelton wheel turbine. Now a numerical on Pelton wheel turbine. In a Pelton turbine installation, the level of water in the reservoir is 500 meters above the level of turbine. The flow rate of water to the turbine is 2 meter cube per second. 20% of the head is lost due to friction in the penstock. Hydraulic efficiency and overall efficiency of the turbine are 97% and 80% respectively. Find out the water power, bucket power, and shaft power of the turbine. So here the head is given as 500 meters, and head loss due to friction is given as 20% of head is lost due to friction. So you can find out the actual head that is available, because you have to take 20% of the available head and you have to subtract that. You will get the actual available head as 400 meters. Discharge is given as 2 meter cube per second, and then hydraulic and overall efficiency is given. So you can find out water power. Water power is equal to rho g QH, where this H should be the actual head that is available. That is, you have to reduce the head loss due to friction. So you will get the actual head, and from there you have found out water power. Then hydraulic efficiency is equal to hydraulic efficiency. Hydraulic efficiency we have written here. Hydraulic efficiency is equal to power delivered to the runner, that is water power by power available at the inlet of the runner power by power delivered to runner, that is runner power by water power. So here you can find out the bucket power. Bucket power is actually runner power. So bucket power by water power is hydraulic efficiency, or runner power by water power. From this you can find out bucket power. Then you have to find out shaft power. Shaft power is a ratio, that is from overall efficiency you can find out shaft power. Overall efficiency equal to shaft power by water power. So using that expression you can find out the shaft power. Next is Francis turbine. Now Francis turbine is a reaction turbine. Impulse turbine we have seen earlier was the Pelton turbine we had seen earlier, it was an impulse turbine. Francis turbine is actually a reaction turbine. It is a medium head, medium discharge reaction turbine. That is a head of 40 meters to 300 meters. So here you can see a scroll casing over here. Okay, this is the main shaft. Attached to the main shaft you have a runner. These are the runners that is attached to the main shaft. Then you have a scroll casing, and this is a guide vane. Here it is marked. This is guide vane. And then here you have draft tube and tail race. So water comes to the scroll casing from the penstock. Water comes to scroll casing. From the scroll casing it passes through the guide vanes. The guide vanes guide the flow, and then it reaches the runner. In the runner the fluid hits on the runner, and then a velocity, where due to the impulsive force, so the fluid hits on the runner and an impulsive force is exerted. And also when the fluid flows through the blades, there is area change in the blades, due to which pressure energy of the fluid is also utilized. So simultaneous utilization of pressure and kinetic energy will exert a reactive force on the turbine blades, due to which the blades will rotate and generate mechanical output. Once the fluid comes out, there can be a chance that the pressure of the, since pressure energy of the fluid is utilized here, the pressure of the fluid can fall below atmospheric pressure. During such a case, it will be difficult to it will be difficult to um, make the water flow out. So you have to raise the pressure head of the fluid to atmospheric pressure. Now that function is done by draft tube. Draft tube is a conical shaped tube. The function of the draft tube is to raise the pressure head of the fluid so that it matches with atmospheric pressure, and we can easily discharge the fluid to the tail race. Now a numerical on Francis turbine. The pressure head and velocity head at the entrance to the runner of a Francis turbine are 250 meter and 10 meter per second. 50 meter and 10 meter per second. So the pressure head and velocity is given. The turbine inlet is 5 meter above tail race. The turbine runs at 400 rpm and discharges 14 meter cube per second of water. Hydraulic losses accounts for 10% of the power available in the water, and the mechanical losses account for 10% of power developed by the turbine. Find out the shaft power and total head across the turbine. Also find the hydraulic, mechanical and overall efficiency. So here we have to find out the total head. So first pressure head is given, that is 250 meter. Then velocity is given, from which we can find out the velocity head, that is v square by 2g. Velocity head is v square by 2g. So v square by 2g will give you the velocity head. This is v square. Then the datum head is given as 5 meter. So h is 5. So total head is equal to pressure head plus kinetic head plus datum head. So from this you can find the total head. Then water power is equal to rho g qh. Q is actually given, discharge is given, density of water we know, and h we have found out. So we will get the water power. Then hydraulic losses in the turbine, losses is also given. So loss is 10%. So from that you can find out the actual power that is available. Okay. So since loss is also, hydraulic loss accounts to 10% of the power available. So you can find out the actual power that is available, that has been found out. Then runner power. Runner power is equal to, actual runner power is equal to water power minus hydraulic losses. So water, when you subtract hydraulic losses from water power, we get the actual runner power that is available, because that loss is known as hydraulic loss. Here it is given the hydraulic losses. So you can subtract hydraulic losses from water power to get the runner power. Then shaft power. Shaft power is equal to runner power minus mechanical losses. Okay, shaft power is equal to runner power minus mechanical losses. Here mechanical loss is also given as 10% of the power available by the turbine, 10% of the power. So once you subtract that, you will get the shaft power. So now we have runner power, shaft power and water power. By using this, you can find out the three efficiencies. Hydraulic efficiency equal to runner power by water power, mechanical efficiency equal to shaft power by runner power, and overall efficiency equal to hydraulic efficiency into mechanical efficiency. Now Kaplan turbine. Kaplan turbine is also a reaction turbine. It is a low head, high discharge reaction turbine working under a head of up to 30 meters. So here again construction is similar to Francis turbine. You have a scroll casing, a guide vane, main shaft. Then here the runner is known as Bose here, Bose. Then you have runner vanes and a large draft tube. So here water comes from the penstock to the scroll casing. From the scroll casing it passes through the guide vanes, which guides the water to the runner. In the runner there is simultaneous utilization of pressure and kinetic energy, due to which a reactive force is exerted and the runner vanes rotate. And once the fluid flows out, there is a chance that its pressure can be less than atmospheric pressure. Then it will be difficult to discharge it to the atmosphere. So the draft tube, which is a conical tube, increases the pressure head of the fluid and it reaches the atmospheric pressure, so that it can be easily discharged to the atmosphere. So this is about hydraulic pump and turbine. Thank you, and wishing you all a happy learning.